Alright, what's up guys? So, this is going to be your notes section for optics and refraction. I'm not going to spend a lot of time going over what I asked you guys to read in section 1. I will, real quick, go back over Snell's law real fast because it's kind of important, and that conceptual challenge questions I wanted you guys to try and do because I think those are pretty important as well. Real quick, just grab a scratch of paper here. Essentially, all refraction is, and I'll say this with words, but I kind of want to show it. So let's just say you have like a surface or a piece of glass here. You got air on one side, and let's say we're looking at an aquarium and you got water on the other side. So light is going to be shining in and hitting this piece of glass. And when it hits the glass, because of the water, you would expect light to continue in the same direction, but because air and water are two different things, two different mediums, the light ray is actually going to bend a bit. And we address these angles, how much we bend by talking about our angles of incidence and our angles of refraction. So the normal line is going to be your perpendicular line to whatever your surface is. In this case, our surface would be this hypothetical glass wall. So our angle of incidence would be the angle at which the light ray is touching or coming towards the glass, and then the angle of refraction would be the angle from the normal that the light ray is traveling inside of the new medium. Now, what distorts this image is a thing called the index of refraction, which you guys actually read about yesterday. There's an equation we're not going to do too much math with, but generally the idea is the variance of the speed of light. So the speed of light is going to be one thing over here, so I'll just say speed of light equals, so V1 equals the speed of light over here, but over here the speed of light is going to be different because you changed the medium. You could actually calculate the index of refraction if you know these various speeds of light, but you don't need to do that. It's kind of redundant. There are tables with these informations. For example, when we talk about the index of refraction in here, N for water is 1.33 index of refraction, and N for air is going to be 1. So by changing this index of refraction, we change how light is going to travel in that medium. So when we see light go from one medium to another medium, we'll see a distortion in the image. A pretty cool thing you guys can do to kind of see this on your own is if you take a clear glass and fill it up with water, and then just take your pencil and add an angle, put your pencil and submerge it in the water. You'll notice if you look at it from the side, your pencil is going to look like it bends as it goes underneath the water there, because you'll actually be able to see from the side of your glass the angle of the angle of refraction compared to the normal line here. You'll actually be able to observe that angle with your pencil. But anyways, just kind of thinking of that now. This is your basic idea of what refraction is. Real quick, 3 minutes here. This, definitely something, if you've never done it before, definitely do it. Just take your pencil, dunk it down in some water in a clear glass, and see it bend from the side. It's pretty neat. But anyways, that's generally what refraction is. Now, I mentioned a few big key vocabulary words there. But what is Snell's law? So Snell's law is the relationship between your angle of incidence and the refractive index of your first medium that your light is in to the ratio of the refractive index of your second medium and the angle of refraction as light passes from medium 1 to medium 2. Typically for us, since we live in an environment filled with air, this first medium is typically air. And the second medium is typically whatever the light is going to. Generally, that's the general idea here, usually. For practical purposes. So, I asked you guys to do question number 1 on page 493. It's a pretty straightforward question. Basically, you have 4 variables, Ni, Qi, Nr, Qr. I say Q, it's the theta, it's theta I, theta R, but still. So you have these variables. So number 1 says find the angle of refraction. So angle R, angle of refraction is what we're solving for, of light that enters a bucket of water. So our second medium is going to be water. So it's going to be for our NR and our QR. We're dealing with water here. I said medium water, I'm just going to label this water. So we're looking for QR and NR in the water. From an air is our first medium, and the light ray enters the bucket. So the angle here in air, which is going to be our angle of incidence, is going to be an angle of 25 degrees. Now we also need Ni, the index of refraction for water. So NR here, I said Ni is water, Ni is air, NR is water. So Ni for air is going to be 1, and the refractive index of water, in this case NR, is going to be 1.33. And since of the 4 variables of Snell's law, we know 3 of them, all you got to do is just a plug and chug problem, plug everything in and solve it. So Ni is going to equal 1 multiplied by the sine of theta I, 25, would be equal to NR 1.33 multiplied by sine of theta R. And that's the whole thing. So all you're really doing is you're typing into your calculator, solve this problem out. I'm going to ignore the ones, doesn't really matter. Sine, let me real quick just make sure that I am in degrees. I was in radians. Good thing I thought to check that. This is not my typical calculator for this stuff. Sine of 25.423 would be equal to 1.33 times sine of theta R. Anyways, shoot, forgot what I was going to do there for a second. My bad. Kind of late here. 1.33. I'm going to divide each side by 1.33. So 0.423 divided by 1.33. 0.318 would be equal to the sine of theta R. And then you're like, well, how do I get rid of the sine? The easiest way to get rid of the sine is just to take the sine inverse of it, because sine inverse of sine theta R will cancel out, and you'd be left with theta R. So on this side, we'll be taking the inverse sine here. So inverse sine of that answer would tell us what angle we're looking at. So our angle is going to be 18.5 degrees, would equal the index, or I'm sorry, not the index of refraction, but the angle of refraction. Now, usually when I think through these problems, I just kind of want to show you guys this portion here. If you're having trouble with this portion labeling, well, what's water, what's air, what's theta R, what's NR, try and draw this out. So you have a bucket of water, based on from the question, and light is going to be entering this at an angle. So your normal line is going to be perpendicular to the surface of water. Your light, in this case, is coming in at an angle 25 degrees away from the normal line. So this is going to be your angle of incidence, 25 degrees. Now, once the light hits the water, it's going to continue traveling, but at an angle of 18 degrees. So I'm trying to draw these lines here. It's going to continue traveling, but at an angle of 18 degrees. So you're going to get this slight bend. So your light ray is going to go, and then it's going to appear to bend. Instead of going straight, it's going to bend very slightly in the water. Expect it to go over here, it's over here. Kind of what this is showing. So all this down here is water, all this up here is air. So Qi and Ni would have to be in the medium of air above the bucket, and theta R and NR would have to be in the medium of water inside of the bucket. So it kind of helps you to know what data you're looking for NR and Ni, those indexes of refraction. The other thing I asked you guys to do as far as reading goes is to read some conceptual challenges. And it does tie directly into this, but still, it's kind of a funny question. And I was looking at it in the movies coming out. A movie called The Invisible Man. It's a horror movie. They made one when I was younger, and they're remaking it now, kind of reimagining the movie a little bit. And you have an invisible man. So, page 491, The Invisible Man, H.G. Wells wrote a famous novel about a man who made himself invisible by changing his index of refraction. What does his index of refraction have to be to accomplish this? Now, generally, I'm just going to draw a very general diagram right here for this. If you have a guy, right, so we have a dude, make him happy. Now, when light hits this guy, if he's invisible, it's going to go straight through him, right? So we're going to have a medium beforehand. This medium is going to be air. Then we're going to have the guy, right, the invisible man, our guy. And then we're going to have the other side of him, which the medium is also going to be air. So air, light goes through the dude, then goes to air. So if this light ray, let's just say it's at a slight angle, goes straight through. Light has to go straight through him without bending at all in order for us to not be able to see him, in order for him to be invisible, right? So the question here says, would his index of refraction have to be to accomplish this? Well, the index of refraction of air and index of refraction of air on each side of him. Well, if this guy has an index of refraction of anything other than that of air, you'll see it bending relative to the normal line. But our angle of incidence here and our angle of refraction here would actually have to be equal for us to not see any bending of light, which means that our in value of incidence would have to be equal to our in value of refraction as well. So basically, the invisible man would have to have the same index of refraction as air in order for him to actually be invisible. Now, something very funny happens here. In order for you to see, skip up here to this, in order for you to be able to see light, your eye takes that light and bends it onto what's called a focal point at the back of your retina. If your eye doesn't bend the light, you cannot see anything. You have to bend light to be able to see. So if you're looking at page 491, there's a second question, visibility for an invisible man. Would the invisible man be able to see anything? Well, if light is not bending at all as it passes through this guy, it means light would not bend at all as it passes through his eye either, which means the guy could not focus any light in his eye. So the invisible man, determined by physics, would have to be blind. He wouldn't be able to see anything because your eye uses refraction to produce sight. And that's actually what we're going to be talking about today in our lesson. Physics notes today is going to be an overview of lenses and refraction. Lenses are just objects that take this property of refraction and utilize it for a specific purpose. We're not going to be getting too much into that purpose, only in the most basic sense of it affects how we see. So how refraction and lenses influence sight. There's a lot more to this, but since we're only doing school from home and I'm very limited on what we could actually do physically with manipulatives, this is how we're going to do it. Kind of break it down and go backwards and very much focus on this. First off, yeah, you have to do some math with refraction with Snell's law. Tough. You'll probably have to draw some of these diagrams if I figure out how to make you guys do that on the test, but probably not. But there's really not going to be much more math with this refraction stuff, but I do want you guys to know how it's used. This is how refraction is used in our bodies. It's how it's useful for us. And we make use of these properties of refraction inherently and then intentionally to correct things like vision. We also use this anytime you hear the term a magnifying glass, a telescope, microscope, any of those things that use lenses, you're using refraction. So I'm using the eye here to kind of model how lenses work and what refraction does. So you've read a little bit about it, you did some math with Snell's law, and then we're going to look at like, okay, so what? How is this used? So, how the eye works. Refraction is used in our eyes. Generally what happens is you have some object over here, just do a box with an up arrow on it. The light rays from this object, so remember light's going to come, it's going to hit this object, it's going to bounce off, right? Reflection, that's how we see stuff. Everything reflects light to some extent. It's how you see things. This light is going to hit your cornea in your eye, and it's going to get bent by your cornea, and then it's going to hit your lens. And it's going to get bent by your lens even more. And those light rays, I just drew one from the top and one from the bottom here, are going to be bent into your eye onto what's called a focal point. This focal point is on the retina of your eye. The retina is the part of your eye that processes visual information and sends it to the brain, and voila, you get to see. In human anatomy, I would love to go more over this, but for now, that's your idea. cornea and lens bend light, focus it on what's called the focal point. So layers come together and you get a focal point, and that builds an image in your brain. So how does this work? How do you focus light? Well, by refraction. Now, one thing to notice here is that you have an error with one value. I'll just say Ni here, since that's the term we're using for Snell's law. Your incidence, your index of refraction of your first media. And then inside your eyeball, you have some fluid in the cornea, and you actually have fluid in your inner eye as well that would have a second N value. We'll call this index of refraction. So you have these two different materials here. Technically, you actually have a refraction going on in the wall of the cornea. You have a refraction going on here, refraction going on here, and refraction going on here. Technically, the liquids are two different types of humors. So there's actually 4 steps to this, not just one, but for the sake of simplicity, bear with me, object, light bends onto the focal point. So we're just going to assume that all of this stuff going on in the eye is just one step. So going from air to the inside of the eye. That's the simplification we'll be looking at here. We're not going to be doing any math with this, just a general idea. So you have this light coming in from air, your first medium, with its own index of refraction. And then it's going to be passing through the cornea, the lens, into the eye with its next index of refraction. This all helps bend the light onto a focal point, and that produces an image in your eye. Refraction literally just means to bend or distort the path of light. So this is how your eye works, generally. Kind of trying to use some of these words. Index of refraction, medium 1, medium 2, air versus the liquid, give you an idea of the bending of light and how you use that to see. This again is why the invisible man would be blind. His eye wouldn't bend any light. Therefore, it wouldn't focus on his focal point, and he would be blind. Couldn't see anything. Now, the thing is, my eyes, and a lot of you guys, if you wear glasses or corrective lenses, your eyes are not perfect either. Your focal point is not on the retina. Well, what can we do about this? Well, we can actually introduce specific types of lenses to help us move that focal point, to focus an image either closer or farther away from where the natural focal point of our eye is going to be. Because remember, our eye itself is a lens, an object that bends light. So, if we talk about someone who is farsighted, this is not me, I'm actually nearsighted, but if you were farsighted, it would mean the focal point would be behind the eye, so that when you see an object without your glasses and it's too close to you, you're actually going to see two objects. You're going to see an object there and there on your retina, where the light intersects the retina, which is going to create a blur in the actual object. Now, if you followed the path that light was traveling, it would actually end up focusing behind where your eye is. So light's coming in, and is focusing behind your eye. Well, how do you correct for something like this, where people who are farsighted? Well, what you do is you actually put a lens in front of that person's eye. Now, the exact shape of these lenses will depend on how much the vision needs to be corrected. But if you are farsighted, the type of lens that will always be used will be what's called a converging lens. So, not that artistic, so bear with me here. The lens would have a generally flat front-facing surface. There would be some curvature to try and match that of your eye. And then on the back side here, you would be doing something like this. So you have this very slight bulge in and out. So it kind of creates, if I just distort this a little bit more, an image or something like this to kind of blow it up. So from the center point here, you would have two sides that mirror out. Now I'm trying to draw what would actually look like in front of your eye. You're not going to have something extreme curvature like you see up here, because you're only moving this focal point very, very small, millimeters to centimeters off. So what's going to happen now is this light coming in is actually going to start being bent before it gets to your eye, and then your eye is going to continue to bend it farther. Forcing that focal point to move. And now the focal point of light is on your retina, and you see only one image for that object. So you have these. These are called converging lenses. They're used to shorten the distance to the focal point. So the focal point of light in your eye was way back here, and then it got closer when you added the converging lens. Basically, a converging lens, the point of this, to converge, it's going to take all of the light rays going into it. So these are light rays. And it's going to take these light rays as they enter in, and it's going to converge them onto one point. So they all converge together. So instead of going straight through, they're going to converge to one point. That's why it's called a converging lens. That is important to know. Basically, this unit is going to be very much vocabulary. Now, the other type of lens you'll see, the other type of condition with your eyes that we can correct with lenses, you have nearsighted, the condition. The other type of lens you can see is called a diverging lens. So the problem being nearsighted like me is when light enters your eye, it focuses to a point too close to your lens and cornea and all that. It doesn't stretch out far enough to get to your retina, which means that you have to extend this angle inside right here. You have to push this focal point back a bit, and you're going to do that by adding a diverging lens. And I'm going to try and exaggerate this a little bit here. So a diverging lens is where you have something like this. So instead of bending outward, you're going to be bending inwards. Now, one side I drew as flat. You don't have to draw one side as flat. You can draw each side with a curve. Just on glasses, this for front side, like I said on the other image, the front side is usually flat, and you're just using this back side to converge to a point by using a diverging lens. Might be a little bit confusing, but I'll show you how these work in physics here in a little bit. But basically what's going to happen is diverging lenses are generally thought of as scattering light. This is a diverging lens that's backwards, and it's going to cause the light that's coming in to strike the eye in such a way that when your eye starts to bend it, it pushes that focal point farther back. So basically, as the light comes in, I did not do a good job at drawing this with the red marker here. I'll try and correct that. I've got another color up here somewhere. There we go, loose blue. So the light is going to be coming into your eye, kind of jacked up this drawing a little bit. So follow the blue lines here. And it's going to diverge it out, so it's going to bend it outwards a little bit. Try and get one in the middle for a normal reference. That way when your eye starts to bend it back, it forces that focal point farther to the back of the eye. And you can see an image. So ignore the red. The red is converging. The blue is diverging. I was talking and drawing at the same time and jacked it all up. It should look something more like this. So as the light passes through, it's going to bend outwards. If it hits it direct on, it's not going to change at all. But if it hits at the sides of this curvature, it's going to start bending out farther. So if I had something over here, it would be farther out. Had light ray over here, it would be farther out. One right here, would be through there. And the thing is, when these diverging light hit the lens in your eyeball, because it's going to, your lens in your eyeball is a converging lens always, it's going to start bending those back to a specific point. And the point it gets to would hopefully be your retina. So this drawing, a little bit small, kind of messed up. This is going to be what happens. So the lens itself diverges or increases the angle away from the focal point of that light. So focal point light is not far enough to the back of the eye to land on the retina for nearsighted people. So we had a diverging lens to spread out the light as it hits your eye. So when your eye is going to focus it, it's going to follow far. It's going to hit farther back. Anyways, that's the general idea there. So this is going back over those lenses with the diagrams that I tried to draw for you guys to show where this focal point is and what's called focal length. And this is where you're talking about it not with an eye. So first off, the lens in your eye is a pure converging lens. So lenses bend light such that they converge or diverge the light rays on a specific point. And this is the last slide of this presentation, if you will. This is the end. This is just the idea. So what is refraction? Cool, you know what refraction is, how lenses work, great, you got that, and that's it. You're ending with the notes today. Granted, I would put forth the activity to you guys to get a cup of water, put your pencil down in it, and actually observe some of this refraction. If you wear glasses, try and sketch your own eyeball out and what's going on there. But yeah. So I could look up some videos for that too. Just figure, you're going to get like a 30-minute lecture notes here. Anyways, so take notes on this stuff, and take a breather, really. Just try and review what you already know about reflection or refraction. Get a little bit confusing. And I haven't went over this page yet. I'm digressing. I'm diverging right now. My train of thought, it's going in all these different directions, just like a diverging lens. So back on topic. Lens has been light. Cool. Converging lens, diverging lens. I've already drawn some of these. But diverging lenses can be a little bit tricky when we talk about focal length. So focal length is going to be the length from the center of your lens to the focal point. Well, a focal point is when all rays of light come together, right? So if you have a diverging lens, those rays of light don't come together on the other side. So how can you calculate a focal length? And the trick here would be to simply take this light ray that's leaving and trace back where those light rays would focus. And this would be a focal point. And you could calculate the focal length through measurement between the lens and that point. So basically, you're taking these angles of refraction here and tracing them back to a focal point. That's just my idea there. Again, there's a lot of stuff to do with this, but yeah, our school year is getting cut incredibly short, and I just kind of want to at least try and hit an overview of all of our main topics for physics. So you're not really going to be doing any of the math with this. If you look at the textbook, there is plenty of math we can do. One thing that's pretty cool that I would suggest doing is just kind of reading a little bit about how cameras work. I'm not going to make you guys do too much or really any work with multiple lenses added together. The eye itself is something where you have multiple lenses added together, but on page 504, if you could, just because I think it's interesting, you might find it interesting as well, read that section about cameras. So just read that page there. It kind of gives you a little bit more of an idea of what this stuff goes on here. And I'll keep you guys posted with notes, and we'll kind of keep moving. I don't know, I seem a little bit squirrely with this because we just found this out today, but the last day for new assignments is May 7th, and we only actually have 4 class periods between now and then, so there's only 4 more lecture/note activities that we'll be doing, and you'll have a test that day. I've just got to figure out what all is going to be on it. And yeah, that's basically where we're at. So I'll keep in touch with you guys, keep in touch with me, and we'll be doing more activities after May 7th. The last school day isn't actually until, I think it's the 28th, so I can't remember, it's the 20-something. It's the 15th for seniors, but the 20-something for everyone else. So we'll kind of see what goes on between now and then, but I think May 7th would be a good day for you guys, because most of you guys are in a pretty good place right now. So just, yeah, electromagnetic radiation, light, reflection, and refraction. And I'll see what else kind of makes sense as far as material-wise to go to add to this. And we got, 4 class periods between now and then. So